Hello, thank you for joining us, and welcome to our webinar with the AI Institute and special guest, Dr. Soroush Saghafian. Dr. Saghafian is currently working on research for stochastic systems with applications in healthcare and operations management. By collaborating directly with hospitals and gaining an understanding of what difficulties the healthcare industry is currently facing, Dr. Saghafian is able to use machine learning and big data techniques to improve hospital operational efficiency, patient flow, and medical decision making. He also serves as a faculty affiliate for both Harvard PhD program in health policy and Harvard Center for Health Decision Science, and holds an adjunct faculty position at the Mayo Clinic. On behalf of the AI Institute, I would like to thank Dr. Soroush Saghafian for joining us today, and we'll allow him for an introduction to his research, followed by a short Q&A session. Thank you.
Thank you very much. Thanks for having me. A pleasure to be here and talk to you. Again, my name is Soroush Saghafian. I'm a faculty member here at Harvard. I teach a large class on machine learning, and we cover a lot of examples of how we can use machine learning to influence some of the biggest societal problems that we have. In recent years, machine learning and AI techniques have influenced how we make public policies. And so today I'm going to give you a few examples of what I teach in my class, some just examples of how machine learning is influencing some of the societal problems that we face and how they are helping us to shape better public policies around those issues. So my class has a large number of people that come from different universities across different departments, from Harvard, from MIT, from Tufts, and from Boston University, other universities. It's a large class. And so we teach both the techniques, but also we show them how these techniques have been used in sort of, again, solving the policy issues and some of the societal problems. And that's what I want to communicate to you today, just give you some examples. And I start my class always by raising this question, or by trying to answer this question, which is, why is machine learning becoming really important these days? And I provide 4 answers that I won't go through them today, but just one thing I want to emphasize today is this, that many of the policy questions that we face, and these questions are very difficult. Usually there are very complicated problem, much more complicated than, beating a human being in a game, is beating a human being in making a good policy. But what we've seen is that many of these policy questions are being answered with machine learning techniques. So here's, for instance, one example: are police bigoted? So are blacks targeted more than the others? And this is one important question, and you see that policymakers and politicians sit around and just discuss their own opinion while there is huge amount of data, and we have all these machine learning techniques that can be used to answer these important questions and shape or policy issues surrounding these problems. So I want to emphasize that, as you know, a lot of organizations are becoming much more data-driven these days. So titles like CDO, Chief Data Officers, did not exist maybe 10 years ago or so, but they doubled from 2012 to 2014. Only within 2 years, we saw that organizations are hiring more and more chief data officers. They are becoming more and more data-driven. So there's a survey of about 1,300 companies worldwide. It shows that over half of organizations are using data analytics every day in their decision-making. There's a study by MIT of about 330 public American companies. It shows that companies that are in top third of their industry in data-driven decision-making, they're about 5% more productive and 6% more profitable compared to their peers. So it's a fact that organizations are becoming data-driven. They're taking advantage of the data that is available to make them more productive, more profitable. And we're seeing same sort of movement within the public sector. So here's another example. For instance, the Santa Cruz Police Department in California is using this machine learning techniques that we have with prediction methods, essentially, to do what is called predictive policing. So what they do is that they try to use machine learning algorithms to predict the areas of the city in which the risk of crime is higher, and this is dynamically done over the throughout the day, and then they share that information with their officers. So you can use, if you do this, you can use your officers, police officers in this case, in a much more effective way. The method they use is called identify and share. They identify first using, again, the machine learning techniques allow them to do good prediction of the parts of the city where the risk is higher, and then share that with their officers. I want to also talk briefly about this article from The Economist, which to me asks an important question. So the question is this: is it time to automate our politicians? Are we ready to have this machine learning algorithms be built in robots and replace our policymakers and politicians with such robots? Now, why do I think this is an important question? Where we have seen that big data and artificial intelligence is making us to make better decisions. I cover a lot of examples of how using AI techniques we're able to beat the best human being in different domains, in different decision-making areas, policy-making areas, and this is a fact that, you know, if we use them correctly, we're able to beat the best human decision makers that we have. They actually ran a poll here in the UK, and they found that 1 in 4 Brits, they think that robots would do a better job than humans as politicians. And this is becoming more and more realistic. In 2018, about less than 2 years ago, we saw that in Tokyo, one of the nominees for being a mayor was a robot. So, you know, it promises fair and balanced representation. And, you know, it has good plans for, you know, you would ask all the participants, what is your plan to reduce the traffic in Tokyo? Everybody has a plan, so does the robot, right? So these things are becoming more and more realistic, and I see a good future for these movements. So what I want you to think about is this: do you think that the robots would do a better job than human beings in the next year, in the next 10 years? And are we ready to move to a situation where our politicians or policymakers are robots? So I want to give you some examples for the rest of the talk about some of the changes that machine learning techniques are have enabled us to do. This is based on my own research with my former PhD student, who's now a faculty member at Harvard Business School. So we were interested to use this machine learning techniques to understand who is an effective and efficient physician. So as you know, in the US, the healthcare expenditure is extremely high. We spend about $9,000 per capita, which is about 2.5 times the average developed countries. And our outcomes are still not as comparable to other countries, the health outcomes. So the question, the important question is that who is an effective and efficient physician? And this is a question that nobody knows, right? So we don't know what physicians are effective, what physicians are efficient. Effective here means that you want them to come up with sort of effective treatment, you know, and understand what the problem is and try to come up with effective treatments for the problem. But at the same time, you want them to be efficient. So you don't want them to use extra tests. You don't want them to use the other hospital resources, waste them essentially, specifically because the healthcare expenditure is extremely high. So we were able to use this machine learning techniques, and what we wanted to do is essentially to be able to classify every physician that the algorithm gets to one of these 4 groups. So you have group 1 being those that are highly effective and highly efficient. You have group 2, those are physicians that are high on efficiency but low on effectiveness, and so on and so forth. So you have these 4 groups, and we wanted to identify physicians that are in group 1, for instance, and then if you do that, you can go to the physicians that are in the other group and tell them, if you want to be efficient and effective, here are the type of things that you need to do, right? So we had access to, you know, performance of physicians in this case from emergency rooms, and you use all sort of machine learning techniques to try to do this sort of identification. And here is, for instance, when we use k-means clustering, we find that these physicians are in group 1, this blue physicians are those that are in group 2, and so on and so forth. Now, this group number 4, for instance, are physicians that are, not effective and not efficient. And when you compare them with physicians that are in group one, in cluster one, now you can understand, you can study what type of things they're doing differently, right? And you can train this group number four to become group number one. If you want to be efficient and effective, here are the type of things that you need to do. Use other techniques, random forest and other techniques, you get similar results. And so this is sort of not sensitive to the techniques that you use. I also want to talk about sort of the ability for us now to use this machine learning techniques to understand crimes. So there's a big data set in the US, it's called US arrest data set, and it includes crime data essentially. So you have number of arrests per 100,000 residents for each state. You have the rate of assault, murder, rape, and other things in each of the 50 states in the US. And so you also have, measures like urban population and other things. And you want to look at this data and you want the algorithm to tell you which states are doing well, which states are not doing well when it comes to sort of crime data. And then also go to the policymakers and say, you're in charge of, let's say, Arizona, and you want to improve, the crime rate in Arizona. These are the specific things you need to do, right? These are the specific policies you need to follow to be able to reach a better state, be similar to a better state. But the first things is that, this data, you want to be able to understand it, and you want to show it to policymaker and make sure that they understand what's going on. For instance, just by looking at this data, you wouldn't know whether Arizona is close to California or not, right? So they are similar in this measure. They are a little bit different in this measure, kind of similar in urban population, but very different in rape, again, percentage-wise. So this dimensionality reduction techniques allow you to make the data set to a size where you can understand it, you can communicate it to policymakers, and in terms of interpretability, they also help you a lot. So for instance, as some of you may know, you can come up with these principal components and then shrink the dimensionality of your data to, let's say, 2 dimensions. And this is very important when you are trying to communicate this insights with policymakers, because if you show them, a 4-dimensional, 3-dimensional graph, it's very hard for them to know what's happening. But by reducing the dimensionality of the data, now you have the ability to do a lot with it. So for instance, even when you show this to a policymaker and they immediately know that, New York and Arizona are close, but New York and Arizona are far from California. And now if they, if New York and Arizona want to be, let's say, closer to California, these are the type of things that they need to do. And so this machine learning techniques help you to also improve your interpretability, make your data set, something that can be understood by policymakers, and come up with policies that are actionable. A lot of times we see that these machine learning techniques are being used and the results are not actionable. You want the machine learning techniques to come up with actionable policies and insights for policymakers that can be used. I want to also talk about, how these machine learning techniques are changing sort of some of the policies that we have around healthcare screening. For instance, this is for breast cancer. This was done in Stanford. Some of you might be familiar with this. These are genomic data. So on each row, we have a gene, and on each column, we have a person. And these are heat maps. The red parts are the genes that are really active. They're working really hard. And the lighter ones are the genes that are not active. They are not working hard. By using these clustering techniques, here specifically, it's hierarchical clustering. By using this specific techniques, we can understand the subtype of the breast cancer. And then that allows us to change some of the policies that we have surrounding how we are, screening breast cancer, and some of the policies that we have that say, oh, if you reach an age of, X, you have to go through this screening system. So I want to also talk a little bit about IBM Watson and how it's influencing some of the things we know for solving, again, societal problems. Let me give you a little bit background. Some of you might be familiar with what IBM Watson is doing. I'm just going to talk about Jeopardy for today. So in 2005, a team of IBM researchers were sort of were trying to develop an algorithm that could compete in Jeopardy. It's a very complex game for those of you who are not familiar with it. At that point, no one knew how to beat humans or if this was possible. At that point, I remember we were working with my PhD students were hired by Netflix to develop these recommendation systems for Netflix, so that now that you go to Netflix, it offers a new movie to you. These are recommendation systems that were sort of hot at that point of time. But at that point, we didn't know that we can beat the best human being in a game like Jeopardy. And that's where the IBM Watson started to sort of grow. And in February of 2011, there was a 2-game exhibition. The winner would win $1 million, and the second place would win a $300,000. Third place would win $200,000. So who are the sort of participants of this game? Well, we have two extraordinary human beings here. One is Ken Jennings. Ken had the longest winning streak. He won 74 games in a row, which is half a year of the show. That's amazing. Brad Rutter had was the biggest money winner. He won over $3 million at that time. Had never lost to a human being, and now you have a bunch of researchers who are trying to beat this extraordinary human beings in this complex game. So what happened? Let me show you what happened as IBM Watson made progress. But before I do that, I want to emphasize that IBM was experienced. So as you know, they were able to in late 80s and early 90s, they were able to develop Deep Blue, which was able to beat Garry Kasparov in 1997. But here is how IBM Watson progressed. So on the y-axis here, we have the precision, and on the x-axis, we have the number of questions that are answered in this game. As you know, the more questions you try to answer, the more mistakes you make, and so your precision usually decreases as you try to answer more questions. And typical human being, well, I consider myself as relatively a smart person, and I believe I'm around here. I have never tested exactly, but I believe I'll be around here. Now, what are these dots? Well, the lighter dots are the human winners, and the darker dot is Ken Jennings, which is the second. Think of him as an extraordinary human being in this game. He's trying to now compete with IBM Watson. And here you see these curves are IBM Watson. So this is where they were baseline. This is in sort of 2007. And in 2010, which is this graph here, you see that it was sort of getting very, very close to Ken Jennings in terms of its performance. At that point, the researchers decided that, yeah, it's ready to compete in this game. And here's the final result of the game, right? So it was able to beat by a huge margin, was able to beat both Ken Jennings and Brad Rutter. Now, why do I mention this example? Well, it's because IBM Watson is changing a lot of different things, not just the game of Jeopardy. So it's changing it's reducing the healthcare expenditure in the US by a lot. So it's being able to sort of contribute to reducing malpractices, which is a huge part of the healthcare expenditure. And the reason it was able to do that is because we have we have huge amount of data, right? So we have electronic medical records, we have medical textbooks and literature, we have more than 5,000 questions from the American College of Doctors Dilemma, which has a lot of examples of different diseases and different cases. So IBM Watson is trained on all of them, and now is able to reduce malpractices using that. But what is important is that I believe in near future, we can go to IBM Watson and also ask this big policy questions. How to reduce inequality? IBM Watson, if you want to reduce inequality in the US, what would you do? How to solve the looming debt crisis? How to decrease the healthcare expenditure? And how to make education affordable? These are some of the important policy questions that we've been dealing with for several decades in the US, and we haven't been able to find good solutions. But you can imagine that IBM Watson will soon be able to provide answers to this. And the reason I'm optimistic about this is that because I know there is huge amount of training data that is IBM Watson is being trained on, and there we have a strong literature for any of those questions. There is tons of published research papers that are available and can be analyzed. So a huge opportunity for using this machine learning techniques to solve some of the big policy questions that we've been dealing with. I also want to make show you another example, which is this using sort of these techniques, decision trees, to learn about how counties vote. And if you learn about how counties vote, you can do a lot for your campaign and for other factors. You can influence how people vote. So this was done actually in 2008, and here the researchers wanted to develop a machine learning algorithm that can learn about how counties in the US vote for the presidential election. And at that point, it seemed that Hillary Clinton's momentum was picking up. So people were like, okay, so is she going to be able to beat Obama and become the president, or at least the nominee for the Democratic Party? And the data set that was available, the training data set that was available at that time was, again, another huge data set. It included a lot of information. This was collected from all the counties in the US where the primaries were done. And so you have in this training data set, you have demographic measures, you have things like, age, ethnic makeup, education, religious breakdown. You also have a lot of political measures in the training data set, things like whether the county voted for Bush versus Kerry in 2004. And you also have a lot of economic measures in the training data set. So things like unemployment rate of each county, you have the amount of construction that is going on in each county, and so on and so forth. So a lot of information in that training data set. And so given all these potential predictors, the question is which one explains the county level voting patterns more? And if you use these techniques, for instance, binary splitting techniques, recursive binary splitting techniques, you find that, well, the percentage of a county that is African American is the most important sort of predictor here. And also that the best splitting is 20%. So as a matter of fact, if you use this recursive binary splitting, you find that the first thing that you need to split over is the percentage of African Americans that are in that county. And if the percentage is higher than 20%, you should predict that Obama will win. Otherwise, Clinton will win. But if you're familiar with this sort of techniques, binary recursive binary splitting techniques, you continue and then you come up with a decision tree that can sort of describe how counties vote. And one of the advantages of this is that it's very interpretable. Actually, you can put it in New York Times. Every person that looks at it can understand it. Right? These are decision trees are very easy to understand. And here you can see that this was put actually on New York Times. It was communicated to policymakers. And as I mentioned, so first predictor is whether the county has more than 20% African Americans. If yes, then the algorithm predicts that they're going to vote for Obama. If no, the second predictor is whether the high school graduation rate is higher than 78%. If yes, then there's another question. If no, the algorithm predicts that they're going to vote for Clinton, and so on and so forth. So you continue until you get a very good sort of decision tree for the prediction you're trying to make. And again, I want to emphasize that interpretability here is vastly important, because you don't want to develop a black box algorithm that has a very good prediction, but then if you communicate it to a policymaker, nobody will follow what you want them to follow. Okay. So then the other example I want to mention briefly is about predicting the outcomes of the United States Supreme Court. So we have now the ability to use this machine learning techniques to also predict how the Supreme Court justices vote and how sort of what is the overall outcome of the Supreme Court. So let me give you a little bit background about the US legal system. For those of you who are not familiar with the US legal system, it operates at both the state level as well as the federal level. The federal courts, they hear cases that are beyond the scope of the state level. And we have essentially three layers of courts in the US. We have discrete courts where they try to make initial decisions. You have circuit courts where they hear appeals from the discrete courts. And then you have the Supreme Court, which makes some of the most influential and difficult decisions that must be made. And the decisions that they make are hugely important. I mean, they have significant level of societal impact. Whether they affirm a case or they reverse the case, it typically has huge implications. They decide about the most difficult and controversial cases. These cases often involves interpretation of constitution. These are not easy sort of decisions to make, but it still has significant societal, political, and economic consequences. The Supreme Court has 9 justices. They are appointed by the president, and they have different views of what should be followed. But with machine learning techniques, we now have better understanding of how the Supreme Court justices vote, and that can have several advantages. Here are some papers that use some of the machine learning techniques to predict how Supreme Court justices vote. If you're interested, there's a huge data set. It's called Supreme Court database that can be used. You see different techniques being used to predict the outcomes of Supreme Court. And these algorithms are doing very well. Here, I just have one example, for instance, for you, where the researchers used 628 previous Supreme Court cases. These are the cases that were occurred between 1994 and 2001. And they made prediction for 68 cases that would be decided later on in 2002. And they put their predictions online so that people later on don't say that there was any cheating or other concerns. They removed those concerns by putting their predictions online before the cases go through the Supreme Court. And the cases here are, the decision is a binary decision. Either the Supreme Court will reverse it or will affirm. But one of the interesting things about this research was that they compare it with human sort of decision makers as well. So they asked a lot of experts, lawyers and other people who are very close to understanding how the Supreme Court justices vote. And they asked the same thing. They asked the algorithm to predict. They asked those experts to predict as well. And then they compared what happens. This is a classification problem. And here you see that with random forest and sort of decision trees, you can come up with also representation of how justices decide. So this is for Justice O'Connor that was in charge at that point. And the decision tree looks something like this. The algorithm says this is how essentially Supreme Court, I can predict what Justice O'Connor does. Is the lower court decision liberal or not? If it's liberal, then the algorithm predicts that the justice will reverse it. If no, then the second question is whether the case is from the second or third DC or federal circuit court, and so on and so forth, right? Now this is very, again, in terms of interpretability, this is amazing because you can show this again to any policymaker and any person involved, and they would get it. They would understand it, that this is, this is very understandable by non-experts. So the overall performance of these algorithms were great. They had their model accuracy was about 75% versus the experts. The human experts had 59% accuracy. This is the overall cases. When it comes to individual justices, the models and the experts were sort of similar. So you see that the model accuracy was about 67%. The experts accuracy was about 68%. So very close for the individual justice predictions, but for the overall case, the algorithm is doing much better than the experts. So here you see that for a lot of justices, these are the justices that were in charge at the time, the model, which is this triangulars, are doing better than the human experts here, right? And these are very promising because it tells us that, you have the algorithms that can understand even the complex decision making at the Supreme Court level, right? And I want to also talk about another example, which I cover in my class, and it's about predicting civil wars. And imagine if you use this machine algorithms to predict civil wars, imagine how many lives you can save. And this is the importance of this type of work, is that you can save a lot of lives by predicting that there is going to be a civil war, and then you can intervene, you can save a lot of lives. So let me tell you what machine learning algorithms tell us about predicting civil wars. The literature that were available in predicting civil wars before machine learning techniques become popular, the literature told us that the civil wars are primarily driven by these sort of collective grievances that are stemming from ethnic diversity and income inequality. So these inequalities and ethnic diversity, lack of ethnic diversity, typically causes this civil wars, as well as income inequality. These were the understanding before machine learning techniques were available. Using machine learning techniques, the picture changed. So newer machine learning techniques, they tell us that that's not true, actually. They tell us that the civil wars are largely driven by the opportunities of insurgencies. So what it means is that the sort of interstate conflicts, they emerge in states, in governments that are not strong enough to control for potential rebellious groups, and where such groups can thrive, the risk of civil war is much higher, right? So this is a different picture that you get using machine learning techniques than all the picture that you had from the previous literature that did not use machine learning techniques. And again, this is an important problem, because if you can do a good prediction on civil war, you can predict them. You can save a lot of lives. And there are, I'm going to just show you two particular models here. The first model uses these predictors, and the second model uses these predictors, again, for predicting civil wars. Let me also show you the performance of this algorithm. So as some of you might be familiar with this ROC curves, an area under the curve, you can look at these measures to see how the algorithm is doing. For the left panel is the first model that I mentioned. The right-hand panel is the second model. And you look at essentially the true positive versus false positive rates, and you calculate the area under the curve, which are AUC measures. So the AUC measure for the first model is 76%, and for the second is about 86%. These are relatively high, and these models are doing well. And of course, there are advancements here as well. So in conclusion, I want to mention that I believe that machine learning and big data analytics is becoming increasingly important. It is making us make much better policies. It's increasingly driving policy decisions. And as you know, many of the public policy decisions, they require dealing with complex decisions. They believe that they are much more complex than playing the game of Go, or playing chess, or playing other games. Beating the best human player in maybe Atari is different than beating the best policymaker. But we are seeing a lot of movements here, and I believe that we have a great opportunity to influence how we make public policies using these techniques. And in addition, I want to add that I teach techniques that allow my students to work with data that is not generated by human beings. So, we have artificial intelligence agents that can create their own data, and we have learning techniques that we can use to learn from that data. And this allows us to move from human data and move to something that can be more reliably used. So in conclusion, I hope I have, in the limited time that I had, I influenced you, I hope, to think more about using this machine learning techniques in your organization, and to try to solve some of the societal level problems that we have. With that, I'm going to stop here and open up if you have any questions for me. My information is here. I'm also sometimes on Twitter and other social media. If you like to be connected, I'm happy to talk to you more. So with that, I'm going to stop, and if there are questions, I'm happy to answer.
Thank you, Dr. Saghafian. I'd like to thank you for the presentation, as it was very informative. And as many of the models that you had discussed are current courses at the AI Institute's bootcamp, I'm sure that many of us have questions. So I'd like to open up the meeting to any questions that anyone would have. I think, yeah, I think so, someone has raised their hand for Bob.
Hello, can you hear me?
Yes.
Okay, Holden, thank you for your excellent presentation, Dr. Saghafian. So my question is in regards to the black box aspect of many modeling techniques, as you know. So in many other areas, such as healthcare, we can use the decisions made by these black box approaches, and we can use such techniques. But in public policy aspects, we want generally to know how these different variables affect certain outcomes. So my question is in regards to using techniques such as deep learning, boosting techniques. As you know, these are completely black box techniques, and how we can really use these techniques. I know there are importance metrics, but these importance metrics are not generally descriptive of how the model learns. I know some of the aspects you have taken, such as the enveloping technique, but I'm not sure if we are ready yet to use such robust techniques such as deep learning in public policy things, as we need to know the hows. Thank you.
Yeah, no, good question. So I'll give you one example from my own project. So I was reached by the sort of CEO of Mass General Hospital, and they have a new technique for treating cancer patients, and this is in healthcare, right? So they have a new treatment for treating cancer patients. It's called proton therapy, and what it does is that you have full control over the radiation, and so you can release it once it reaches the tumor. So it prevents from ruining the surrounding tumors and things like that. But the demand for this is like extremely high, and there is, MGH has 3 machines that can do that, and many other hospitals, most hospitals don't do that. So in other states, it's not available, but everybody can apply to receive this treatment. And the high-level hospital wants to have an algorithm that can predict who should be accepted for this, right? You have a billion number of people are trying to get to this treatment, but you have 3 machines that are available to do that. And but you can develop an algorithm that was the goal of what we did for them. We developed an algorithm that does a very good job in understanding and predicting, if you give it to this person, it's not going to be that useful because the person is going to die either way or for other reasons, versus if you give it to this other person, it might help them a lot. And based on that, the algorithm decides whether, to accept the application or not. But, it turned out to be sort of black box, although we tried really hard to get away from the black box. And, once it becomes to the level of implementation, even at the hospital level, you're trying to implement that, it becomes very difficult because, if a person dies and because the treatment was denied for them, they can go to, form a lawsuit and come back and say, well, why did this algorithm, deny it, my treatment, and give it to this other person? And so here are the cases where interpretability becomes important. And in public policy domain specifically, it's hugely important. If you go to a policymaker and say, oh, I have this convolutional neural network that can predict X and Y and Z, but I can't tell you how it's making decision. They have to have a fair representation of their people, and so they might not be able to follow that, even if that is good. But beyond that, also you should notice that not all of the policy questions are are prediction problems. Some policy questions are prediction problems. Some of them you need to have go to causal sort of techniques, and beyond interpretability, have the ability to do also causal inference on top of what the algorithm is doing. These things are complex, and so still are active areas of research for us to understand how to have, how to be able to use those black box algorithms, but also have good level of interpretability, so we can use them in public policy domain.
Thank you. Are there any other questions? Okay, I have a question from Matthias. I wanted to ask about what you think is the most difficult obstacle for people who graduate from a hard science background to move into public policy. Is a field completely dominated by people who come from a more traditional background, such as economics or public policy?
I think, I think there's a huge amount of opportunity for hard science, like scientists, engineers, to move into public policy and influence how public policy decisions are made. These are, again, the similarities are that these are complex decision problems that need to be solved. But at the same time, in social sciences, the difference is that you need to have an understanding of how things work, right? So in the engineering domain, if you're trying to solve a problem, you need to have the best tool. But in social sciences, it's not just about developing a better tool, right? So developing a better algorithm is not the only thing that you need to be worried about. You need to be worried about, like, other things, as I mentioned. If you're trying to predict civil war, there are several other aspects that you need to care about and you need to understand, besides just, that I have a better algorithm that you have. That's different than, developing an algorithm that helps Netflix, and understand your preferences, right? So some of my students with engineering background, for instance, they are hired by Netflix. They have years of experience in developing these algorithms, and now when they want to move to public policy and try to solve societal problems, essentially, they lack that background of understanding the differences. Things that are important for Netflix are not going to be that important for a policymaker who cares about different dimensions. So this multi-dimensionality of the problem, that the problem has a lot of criteria that you need to take into account. It's not just that, for the Netflix, what they want to do is that just understand the preferences of the customer better. That's, well, there are other things too, but mainly you can summarize it like that. But if you're working with a policymaker, the decisions that they have to make has a lot of aspects, multi-criteria, very complex. The criteria influences each other. And so you have to have the domain knowledge a little bit. But at the same time, I believe, people from engineering, from physics, from computer science, from other related backgrounds, mathematics even, can be very helpful in this domain.
Thank you very much. Actually, I had a question as well. In your experience working with policymakers and presenting them with these models and different ideas, how open are they generally to taking advice or taking influence from these high-level machine learning algorithms?
Yeah, so they are open. They are very open, as long as, at the end of the day, if they are in charge, again, they need to understand how the algorithm is making decisions. They're highly, I think, worried about biases of the algorithms. They're highly worried about, the black box aspect of the algorithms. They're highly worried about, being able to protect their people in different dimensions. Having a fair representation is another important aspect. At the same time, I think they understand. So I have policymakers even coming to my class, and when I show them that, the algorithm that is able to, beat the best human player in the game of Go, for instance, and then they start thinking, oh, we can use this to solve this problem specifically that we have if we can resolve some of these other aspects. So I think they are very interested. At the same time, I believe they're worried about, rightfully, about things like, making sure that the algorithm is not biased, making sure that it provides a fair representation, and making sure that, for instance, when I ask them this question of whether you think, the robot can replace you, right? the answers are mixed because, you know, it is a complex, you know, they have to make complex decisions, and they are not sure whether the algorithms are at that level that they can make those level of complex decisions. But at the same time, they are very open to it. I think I've seen a lot of interest, and it's because they are seeing more and more of this coming from the private sector to public policy sector, right? So I mentioned the police department, for instance, using this techniques for predictive policing. So a lot of things are happening, and that makes them, you know, more excited at.
Hi, Dr. Saghafian. Actually, I have a question regarding the logistics and public policy. Do you have any any examples regarding the linking between these two areas?
Yeah, so, you know, supply chains and logistics specifically, you know, there are important parts of, I think, public policy. You know, let's talk about vaccines for COVID-19 and a lot of different things that are going on for COVID-19 in terms of ventilators and other things. There are logistic questions that need to be decided. So I think there's a huge link between the logistic issues and the public policy, but you know, the level of understanding needs to be different than, you know, in if you're trained in, let's say, logistics, you may care about, you know, optimizing the holding cost of the inventory, or you might be, you know, optimizing the, you know, the routes that you know, you're taking, and the travel distances and the travel costs and things like that, logistic costs. But when you come to, you know, public policy level, the criteria changes. So I think, you know, a lot of those techniques are helpful, but you gotta have the understanding of what, you know, policymakers care about more than the logistical criteria. So again, I think it boils down to the criteria that I think becomes important at the policy level. That is different at the, you know, business level or at the local level. Those are sort of different criteria.
Sounds good. Thank you. Because I was thinking about the car sharing or in general sharing economy and the effect on the government, like the taxi services or something like this one.
Yeah, at that level too, you know, the gig economy is moving towards public policy, and there are several questions. You know, people are you know, trying to, you know, even at the Congress level, they're trying to decide whether they should increase restrictions on the gig economy, or, you know, try to, you know, sort of control what is happening with Uber and other companies in terms of ride sharing and those techniques. So these are all, you know, important questions. But again, you know, the criteria for Uber is minimizing the cost. The criteria for public policymakers is not just minimizing the cost. They care about other, you know, societal level metrics that companies don't care that much about. So if you want to study that problem, you have to have an understanding of the correct criteria.
Sounds good. Thank you.
Yeah, of course.
Hi, good afternoon. I have a clarification I would like to have, because you've been talking a lot about algorithmic. As of now, we have existing algorithm that we use to build predictive models. So I want to be clear that, are you talking about creating new algorithm or improve existing algorithms? So what is the point? Because I get confused about where you presented.
Good question. So it's both. You know, sometimes the available algorithms are good enough. If you can, you know, use them correctly, they might be good enough. But sometimes you need to develop new algorithms for new problems as well. So I think it's both of them. And depending on the problem, you know, you may see that the existing algorithms don't work well. So you need to develop your own algorithm that does something, right? But, you know, we have huge number of algorithms, techniques in machine learning, in artificial intelligence, in optimization that are available out there. And that's the starting point. I mean, you know, for the problem, you should start with the existing algorithms, see which one works best, which one doesn't work. And sometimes, you know, you'll see that almost all of them don't work. And so you have to develop your own sort of algorithm and sort technique.
All right, thank you. But that goes beyond of I mean, you know, as a data scientist, which is on training now, we learn to use existing algorithmic to build our model. But so that means we have to go beyond that and be able to
Absolutely,
create your
absolutely.
own code. All right, thank you.
Yeah, absolutely. You know, because these questions that I'm talking about, some of them are very complex questions. And so if you just want to use available techniques, you may get halfway, but you cannot find sort of the good solution, right? So sometimes you have to develop your own algorithm and try to even develop new techniques to address that problem, right? So again, I think this fact that a lot of these problems are multi-objective. You might have some of them, you know, you might not even know the objectives, and you're trying to optimize without exactly knowing the objective or having, you know, data on that objective function. How do you optimize that?
Thank you.
Thank you, Dr. Saghafian. I have a question about, because I am looking for combining like convolutional neural networks and deep learning in general and operational research models in order to address the humanitarian problems such as humanitarian logistics or facility location, to help maybe poorer areas where people need help about food, about whatsoever. So my questions are, first, have you previously worked on using like convolutional neural networks and computer vision mixed with operational research models to solve like humanitarian problems? And more importantly, do you envision any future for that? And the second question is, because now I am starting to do some literature survey to see what works have been done. Is it possible to follow up with you about like the domain and the work that could be done hopefully in future?
Yeah, so again, another good question. And I believe, you know, so the deep learning techniques have, they can play an important role in logistics and in humanitarian sort of research questions. So I have PhD students who are working with satellite images. I have students who are working with in the sort of other domains, looking at the pictures of, you know, people who are going to Supreme Court and understanding like what the skin color plays a role. But, you know, in the healthcare area, for instance, they are using the satellite images to understand how the built-in environment impacts, let's say, the obesity. Or you can study, for instance, how the built-in environment impacts logistical disruptions that happen for, you know, if you want to say provide water for poor areas, right? So you can use satellite images to understand the built-in environment better, and, you know, use those deep learning techniques to analyze those satellite images in a better way, and then, you know, understand what is causing logistical issues that are out there. So these are just a couple of examples I'm giving you, but, you know, the field is not limited to these things. There's tons of things you can do. And then the second question, I'm happy to help as much as, you know, the time allows. Yeah.
Yeah, thank you, Dr. Saghafian. Thank you so much.
Of course. Yeah.
So I have another question. My question is similar to one of the earlier questions, but so one of our friends asked about the people from hard sciences backgrounds and their involvement in public policy and AI. My question is somehow different, that I have the same question for people from health sciences, people like for the clinical backgrounds, people like public health backgrounds. Would like lower mathematical knowledge be a barrier for them, or how they can work in this environment? I wonder. Thank you.
Yeah, good question. And, you know, so I have MD doctors that work with me, and they're sometimes PhD students, they come to get a PhD degree, and that's a common question. And my view is that, you know, you can contribute by leveraging what you know best, and then try to learn from other areas, right? And that can be a very good combination. So, you know, if you're working in health domain, if you don't have, you know, the clinical knowledge, that's going to be a problem. So, but if you have the clinical knowledge and then try to also learn the algorithms and combine them, and, you know, then you can do a lot. So my view is that you should consider what you know differently than others as an opportunity rather than as a problem, but try to add what you don't know. That is, you know, you can learn those things, but what you already know, try to use that in your advantage. So try to think of that as an opportunity that you have, right? Rather than sort of a disadvantage. And that's usually, you know, where the innovation happens, is that you combine different, you know, knowledge, and you gain things that you don't know, but you contribute to that know. So let's say if everybody in this domain didn't have any clinical knowledge, and so everybody was like, you know, working on algorithms to develop things for the healthcare sector, and nobody had the clinical knowledge. And then if there's a person that both knows the algorithm and knows the, you know, the clinical side of things, then that's a huge opportunity, I think.
Thank you. Thank you very much.
Yeah, of course.
Are there any other questions?
Let me ask the last one. Good afternoon, Dr. Saghafian. My question is that how do you guys involve the uncertainty in policy making? I mean, that's a different thing change, like political parties and this kind of thing, and how we can involve the policy. I mean, that's different changes in policy making, and how you guys, I mean, that assess the risk in this kind of thing.
Yeah, good question. Yeah. So I think, you know, I see personally, I see a lot of value for the approaches that consider ambiguities and try to be robust to what is unknown. So a lot of, you know, algorithms, they are not robust, and they are developed for specific, you know, use and things like that. But you have algorithms that take into account those type of uncertainty. They try to be robust to changes intentionally, and so you optimize given sort of an uncertainty set and things like that, and try to be better in that sense. And those are typically very powerful techniques. And, you know, a lot of times you try to be robust to things that can change, or have adaptive solutions. So the adaptive solutions say, okay, so the algorithm can adaptively, you know, optimize things. When things changes, it, you know, provides a different solution.
Okay, thank you.
Yeah, of course.
Okay, thank you so much for joining us. I'd like to thank everyone for joining us with this presentation by Dr. Saghafian and the Q&A session. And I also like to, on behalf of the AI Institute, like to thank Dr. Saghafian for taking the time to speak with us today. I know that it was very informative for me, and I speak for, I think, everyone else who comes from a machine learning or is interested in machine learning, learning about machine learning. It was very beneficial for us.
Thank you for having me. A pleasure for me.
Thanks.
Thank you.
Thank you.
Bye.
Thank you so much.
Thank you.
Thank you so much, Soroush.
Thank you.
Thank you. Thank you.